Now that we have a pretty firm understanding of the theory of gases, we're going to get more of an understanding of the real gases. To do this, we're going to need Dalton's law of partial pressures. It says that the total pressure is the sum of all the pressures that compose of that. It's really used for mixtures. The most common mixture you encounter is air. Air is a mixture of nitrogen, a little bit of helium, oxygen, carbon dioxide, and a couple of other trace gases. And so we can actually use those pressures and convert them, pressures using the ideal gas law, into nRT over V, and use the sum of those as well. So it doesn't really matter what the gas is. Now, the sum of the total pressures will equal the sum of the total moles. And that's a very useful thing since the volume R and T will remain constant. Those don't change. It would just be the number of moles and the pressures that would actually change in a mixture. And that's very useful when we run into it in real life. When we're looking at in a mixture of gas and we're looking at all the different moles of different gases, we can use what's called a mole fraction, symbolized by the Greek letter chi. It looks like an X, but it's chi, and it's chi 1 is would be N1, the number of the first gas, divided by the total number of moles of all of them. And you would also have a chi 2 would be N2 divided by the total. A chi 3 would be N3 divided by the total. And since the mole fraction can be used to manipulate and specifically identify the ratio of how many moles to a total number of mixture, we can actually and rearrange the variables so that the pressure of my one gas will now equal the mole fraction times the total pressure. We most commonly run into Dalton's law when we're collecting gas underwater, because as the gas will bubble up and be collected in this tube, we'll also get a partial pressure of the water vapor as well, and we have to take that into account to understand the total amount of pressure. So you would get the pressure of your gas would be coming through here and it would be bubbling up, but as it bubbles up it will pick up some kind of water vapor, so that would be able to explain some of the error that you received, or the experimental error you received. This is a common Dalton's law problem, and go ahead and pause and give it a try. See if you can draw some pictures to help you along. I've drawn some pictures and I'm going to go ahead and write in some data as I go along. So I know that my oxygen was at 0.2 liters and 0 degrees Celsius and 1 atmosphere. If I notice that 0 degrees Celsius doesn't change, so if it doesn't change, just exclude them because they're not going to be factors in the calculation. So if I'm going to put a 0.2 liters here and a 1 atmosphere. Excluding sig figs just for time. And I put a dead baby in there, but okay, I'll just put a 0. So 0.2 liters and 1 atmosphere. So let's put our nitrogens in here, and that is going to be 0.1 liters, and then it's going to be 2 atmospheres. So at 2 atmospheres. These two are individual containers, and they are going to be placed into our new container. So these two are going to be placed into this one. And this one has a new volume of 0.4 liters. and we want to know its pressure. So we want to know the atmospheres. Okay, so what I suggest you do is now that you see this, you can we're going to involve a different gas law to help us along. We're going to involve Boyle's law, because this we have volume and pressure, so we have PV. That's Boyle's law. So we'll use Boyle's law as our equation, and we'll look at oxygen first. As it goes, and this would be our initial conditions, 0.2 times 1 here, and it equals our final conditions of 0.4 times my unknown amount of atmospheres, my unknown pressure. So my unknown pressure is now going to be 0.5 atmospheres as my pressure of oxygen. Now I will have the same thing for the nitrogen. These are my initial conditions of nitrogen, and they will move into my new container of 0.4 liters here, and that will help me solve for my unknown pressure as 0.5 atmospheres of nitrogen. So now the total pressure will just be the sum of those two, and I can find out that the total final pressure is going to be 1 atmosphere.